Hello folks, this is tutorial 3 in the playlist which is called the buckling analysis with 3D experience. This tutorial 3 is actually a follow-up to tutorial 2. They're related and I will briefly review what happened in tutorial 2. So we have first of all, the information is taken from this site, from this YouTube video at University of Alberta, and the first part of this lecture, which starts at 103, I believe, uh, deals with the linear buckling analysis of an I-beam column. Okay? And that's what I did in tutorial 2. Okay, so here's the situation. We have an I-beam, these dimensions, 5,000 millimeters long, 5 meters long, and the bottom of this clamp and the top is subjected to a compressive load. Remember, these are not forces here, these are the local axis of the beam cross section. Now, if there is any nonlinearity involved, such as imperfections, material nonlinearity, contact, etc., the result of a linear buckling analysis is just not valid. And you have to do a nonlinear analysis. And nonlinear analysis needs to be done with the RIKS step method. Okay, so uh, this is exactly what I said. In the present problem, uh, we're not going to assume there is no contact and there is no material nonlinearity. But let's say we didn't know these things. Okay, so what you want to do is actually go ahead and repeat that calculation with the RIKS method. However, keep in mind that the buckling analysis, linear buckling analysis, predicted a load of a critical load of 7.4, I believe, 10 to the 6 Newton. Let's pretend we don't know that, okay? Now, in this video tutorial down here, starting at 137, the RIKS part of the uh, uh, tutorial is starting, okay? I will go through this thing very quickly because these were discussed and talked about in tutorial 2. There's no sense in actually go ahead and repeating it here. As a matter of fact, I'm neither going to create my model nor mesh it nor material. I'm going to take the stuff that I did in tutorial 2 and just delete the buckling analysis and or just go ahead and insert whatever I want. Okay, so these are things that were in tutorial 2. So this is the Euler critical buckling load, which we are not going to use because we don't know. We want to do this thing with RIKS analysis. So when you do RIKS analysis, you apply a load, for example, but you don't know what that load means in the sense that it may be higher than the capacity that it can carry, etc. So that's called the reference load. Now, the reason I'm choosing, or the reason that the YouTuber chose 8e to the 6 is that he said, okay, if I do a hand calculation, I get a buckling load of 7.2 e to the 6 or 7.4 e to the 6. Why don't I use something that's even slightly bigger than that? So this is a reference load in RIKS analysis. Now, you will see that at some point, that number 7.42 or something close to it is going to pop up. Okay. Now, here is the structural scenario creation, or you can do that in mechanical scenario creation. And there is a RIKS analysis, a RIKS step, static RIKS step. But in order to do that, I will first introduce the imperfection into the I-beam by moving it a little bit to the right, okay? And because if you just compress that thing, even with static RIKS, it's not going to buckle. Okay, you have to create some kind of an imperfection into it, and the way imperfection is introduced in this problem was by pushing it to the right slightly. Okay, Essentially, the I-beam takes the form of the first mode of buckling, linear buckling. Okay, or you can do that in mechanical scenario creation, but I'm going to go in the first one. I have already discussed this and showed you how to display uh, the the cross section as a 3D basically drawing for a wireframe, and then I come back and talk about this thing later on. Okay, in other words, some of the parameters I'm going to change, specifically this number 1, but then I'm going to come and change it to 0.1. We'll get to that later. Okay. All right. So let's go ahead here. This is what I did in tutorial 2. I'm not going to use the simulation because here I use the linear buckling step. We can see that in the scenario right there, buckle step. Either I can delete this or I can start fresh. And that's exactly what I'm going to do. So I'm going to delete this simulation, and this is my model. This is the model that was created with in tutorial 2, and there is a 50 beam elements along that length. Okay, so we start at this point. If you wonder what happened and how did I do this thing, please watch the first few minutes of tutorial 2. Okay, so let's go ahead and to structural scenario creation. All right, we are using that mesh. All right, good. Now notice that there is no procedure exists. So here's what I'm going to do. I'm going to go procedure. First, I push this thing in the Y direction. So that is going to be my first step, and it's going to be linear static step right there. Static step. Static step. And I will leave these things as default. Okay. This is going to be nonlinear, of course. Notice that uh, this is checked by default, so it's going to be a nonlinear calculation. Material, by the way, was just linear elastic for steel. Okay, good. Now, no longer we have a red exclamation mark here. So let's go ahead and apply our boundary condition. So we go with boundary conditions. Uh, let's go and apply a fixed displacement at the very bottom of this, which means this line. Essentially, this line is my beam element. This blue stuff that you see here is for visual purposes. As a matter of fact, I can turn it off, and I'm going to show you, remind you how to do it if you want to turn it off. So this is checked in all 3 directions, fixed in all 3 directions, both translation and rotation. Okay. All right. Now, if you don't want to see this, let me remind you what we did. We went to the display, under display preferences, and there is this in this portion of the dialog box says beam symbols. Right now it says solid. If I turn this thing to none, you just see the line. Okay. And if you don't want to see this coordinate system here, the local coordinate system, uncheck that and say fine. There we are. If that makes us happier, this is fine. Now let's go back to our scenario, which was here. Okay, and then we're going to go to again boundary condition. That line is going to be restricted from moving in the x direction. So we're going to go again boundary condition, fixed displacement. That entire line cannot move in the direction x, and these rotations y and z are opposite. That means that essentially I have a two-dimensional problem. Okay, in other words, essentially I have a B21 element as opposed to B31 that I have. This replicates the stuff in that the element that's used in that tutorial from University of Alberta. All right, good. Now we're going to apply by the way, these things that I'm doing are appearing. You can see that they are appearing in boundary condition. These are the two things that I did. Okay. Now I'm going to push this thing to the right by a force of 1 Newton. 1 Newton is nothing. It's just to give it a slight imperfection, a slight bending. So we're going to go to load, force, this guy, this point, in the direction 1 Newton. There we are. Now, if I run this thing, nothing fancy is going to happen. It's just going to bend to the right. I can run it now and show you what happens, or we can do the static RIKS step and show you later. Let me run it and basically look at the result, and then come back and add our second step, which is static RIKS. Okay, so how do we do that? We go to simulate. First of all, model and scenario check. I don't anticipate any problems unless I forgot something. Good. Let's do a simulation check. All right. Okay, it's almost done. These things are counterpart of the data check in the ABAQUS program. Okay, good. And then we're going to run it. Nothing fancy. It's just going to bend to the right. Right meaning in the y direction, because that's the direction where I'm applying my force. Okay, finished. And it's such a simple problem, it's going to do it itself in two steps, take a gigantic step and solve the nonlinear problem essentially for us. There is no nonlinearity here. So let me close that. If you want to see this, here is the first step. This is a von Mises stress. Okay, notice that pretty much it's almost zero, right? 1 Newton for a beam, 5 meter, and that cross section, it's not going to put any stress in it. Okay. If you want to look at the deflection, the displacement, you might say, well, why is it not going to the right anyway? Let me change the view here. View. I'm going to change that thing to from the front, not to view. I'm going to look at the view from the front because this is a two-dimensional problem. There's no reason to look at it in 3D. You might say, well, how come it's not moving to the right? Well, I mean, these displacements are so small. And let me double click on it. Double click on the contour, anywhere on this contour, and select this second tab and says scale factor. Let me make the scale factor 10,000. Oops, that's too many. 10,000. Let's see how it looks like. Apply. It still didn't look much different. Let me put another 0 here. Apply. Ah, you see that? Let me do another 0. It's going to be big jump. So it is actually moving, but the deflection is so small that you have to use a scale factor which is very high. When you do nonlinear analysis, it is set automatically on 1. But anyway, this is closed. Let me close that. All right, fine. Now we are happy with this, okay? And let's go ahead back to the scenario. So click on the standard tab. There's a scenario because you want to include our second step, okay? So under procedure, there is static RIKS step. Static RIKS step. You click on it. Okay. Now, a couple of things I'm going to do to be consistent with the YouTube video from University of Alberta. I'm going to change this thing to 100. And the gentleman there takes this thing to be 0.01. And this thing, maximum arc length increment to be 0.5. Okay, everything else. Oh yeah, stopping criteria. I'm going to click on the stopping criteria. And for maximum load proportionality factor, he uses 1, I use 1. You say, okay, good. Notice that we now have a RIKS static step, and notice static RIKS step, and notice what happened is that these two displacements also propagated through that next step. The first force, which was pushing to the right, got propagated to the second step, and now we want to compress this. So we go to loads, force on that top point in the direction z. We put minus 8e to the 6 Newton. Okay, so this, what you see here, is that reference. Let me see now, that reference value that I was talking about. Okay. All right, good. So let me save. Okay, and we're gonna I'm gonna do a model check. No problem. I'm gonna do a simulation check. I'm pretty sure it's no problem. By the way, Rick's method is the same as some variation of arc length method. And Ricks was a gentleman who was working in one of the research labs in the States. So that's where the name is coming from. We say fine, and now I'm going to run it. So I want to do a couple of things after it finishes. We'll see. After it finishes, uh, the YouTube video from Alberta is going to try to plot uh, force versus arc length and displacement versus arc length. But there's some issues that are going to arise. That's why the presenter indicates that there's something wrong, okay? And he doesn't spend the time during the lecture in order to find out what is wrong, although he does mention something in his uh, uh, screen on the presentation, but shows instead the result of a run that was made earlier that day. And okay, so that's good. So let me close this. All right. So this is static step 1. You can see that. Okay. Now I think my scale factor is 1/10 to the 6. I may have to reduce that. You'll see why. If I go to step 2, there it is. Notice that it is so big that actually makes you think that the beam is going to go down. So what I'm going to do is I'm going to do the following. I'm going to go back there. I'm going to change the scale factor to 1. Okay, good. This number matches exactly what the YouTube reference predicts. Okay, now, what I want to do is I want to plot force versus arc length and displacement versus arc length of that point. So we go to plots. Okay, we go to plots. We have to extract the data. So let me also deactivate this plot that I see there. Let me go to results, plots. I'm going to deactivate this. Displacement I'm going to deactivate. Okay, and there is a reason I did that, because I want to pick a node on the very top, and if that already deformed, it's not going to give me exactly the point on the top that I want. That's fine. So we go here to down here under plots tab, we go to XY plot from field. Okay, now I'm going to select the point, the node. The node is going to be the one on the top. It better have coordinate 5,000. So if I click on this pencil, it gives me the coordinate 5,000. Okay, good. So I picked the right node. Now, I don't want all frames. I want the frames of step, and the step is Rick's step. I want to show this plot to you for the RIKS step, because there's nothing fancy about the result in the static step. It's going to be just straight line. Okay, there's nothing fancy there. So we don't want that. Okay. We change this fellow to the displacement template, translation, and the YouTuber, I don't think he meant it, but he selects displacement in the direction. I believe he takes some direction 2. Okay, direction 2. Direction 2 for us it is moving to the right. Why? Okay, that's good. And then we say okay. So this plot, which is displacement in millimeter versus the arc length. It uses arc length because I selected it from the RIKS step. Okay, this matches the ABAQUS CAE results from that YouTube video. Okay, so let me close that. And I'm going to, these plots that I'm generating, I'm going to deactivate them. Actually, I'll leave this thing here, no problem. I'll do another one. I go to the XY plot from field once again. And for the node, I select that same node. You see that? Let's check, make sure it is actually coordinate 5000. Because if I do bring it down here, it selects a different node, no problem. And the template is reaction force. And what I want is the concentrated force. And I think, again, that reference chooses direction 2, which probably was not intended. You say, okay, deactivate existing plot from the current chart. No, don't deactivate because I want both of them to be on the same plot. There we are. Okay, this, let me check that. Something about this one. Oh, okay. When I did this guy, I forgot to choose the RIKS step. So let's go back here. Yeah. Not all frames. All frames in step, and the step is RIKS plot or RIKS step. There. This matches the results in the ABAQUS CAE. Okay. And at that point, the YouTuber says, wait a minute, this doesn't look right because I ran it earlier today and it was different. So he says, I think the problem, he indicates that I think the problem is in the arc length value that I specified. There is one thing that's bothering me here. Oh yeah, okay, so you can see that during that RIKS step, the load to the right is 1 Newton. We know that. It stays. It comes from step 1, which was 1 Newton, and it stays like that. He says, okay, I don't think this is what I wanted. And he says that maybe I made a mistake. And then opens up his video from earlier that day and shows you a plot, and I'm going to regenerate that plot based on changing this value to 0.1. Okay, that's all. So you go here. Let me go double click on this. Where is that thing? RIKS, static RIKS, double click. And this number, I'm going to change it to 0.1. And then we say, okay. Okay. We're going to have to run it. Let's run it. Remember, in the first step, the time is the parameter. In the second step, which is the RIKS step, is the arc length. That's the parameter. That's why you have to be careful when it comes to these plots. As a matter of fact, in the CAE code that this gentleman uses, says, oh, I have to go and deactivate the ABAQUS static step because you cannot mix them. I don't have to do that because it allows me to select it from that pull-down menu. Okay, that's pretty much it. This is almost done. Extracting results. All right. Okay, so it goes a lot further. Oh, I think so. We say okay, close that, and I close this. Now I go here and let me look at this plot, for example. See how they change. They do change. I have to go, and when I try to plot that, it says, you know what? Are you basically have to reset this thing. See, it says all frames is invalid. So I'm going to go from RIKS step. Say okay. There we are. Let me close that. Let me go to the other one. Again, it says this is not valid, so we go static RIKS step. There we are. Okay. And the one thing that you notice that actually the problem is that both of these plots, this should be downward. I took it in the direction 2. Let me see for a second. Let's see how we did this thing. Let me go and double click on this. This is direction 2, direction Y. Okay. The question is, I don't want direction Y. I want direction 3. Because that's what I'm saying. The choice of those selections in the YouTube video on ABAQUS CAE may not have been quite what he wanted. So I changed this thing to component 3, downward. And the same thing down here. Same thing down here. Where is that? Did I do this? No, vector component 3. This is for the force. Okay. The only thing is that this, you see that plot, is not what he has. As a matter of fact, let me do the following. Let me go there. It was let me. This was force. Nope. That guy is. Let me see. I think he kept that in the direction. It should be direction 3. I mean, force deflection should be direction 3. That's okay. Let me say okay. Now, these are force and displacement versus arc length. But I want force versus displacement. And the way that is done here, you go to plot from expression, XY plot from expression right here. And then you select this f of x right there. You see, these are so different from how things are in ABAQUS CAE. It's impossible. This is combined. This displacement versus that force. So plot of displacement, not versus arc length, displacement and force. Okay, so we say okay. All right. The only thing is that that is not what he has. So let me do the following. Let me go back here. Let me go back here. Not there. Let me go back, and I'm not sure. Let me just check this. Let me try component 2, see whether that is what he's showing us. Activate this. Yeah, exactly. Notice that this number 7.4 popped up here. This curve matches what he generates after these manipulations. Okay, so what I'm telling you is this: I don't know why he's plotting. He should be plotting force in the direction z, and this one also force in the direction z, but he's doing direction y. I'm not sure, but I wanted to reproduce for you. So let me deactivate these. Let me show you again. Deactivate this, deactivate that, and there. This matches his plot. And it shows you that I did not know anything about this buckling load of 7.4. It pops up by itself right there. So there's buckling here, and then there's a sideways deflection. Now, and he makes a very good point. He says, well, I mean, look, if you want to get this 7.4, why did you have to do all of this? I could have done an eigenvalue calculation and come up with a buckling, critical buckling load. The problem is that if you have any nonlinearity, that number that you get from linear buckling analysis will not match this number. Okay, so you'll have to do, you have to be very careful and do nonlinear analysis. I mean, yeah, we were just kind of lucky here that although we did have some imperfections, still it was close enough, So you got to be careful. Linear buckling analysis is cheap, but it will give you a very um, a value which is very approximate and is usually higher than the actual buckling load. Okay. Nonlinear analysis is what actually gives you if it's done properly, it's going to give you the correct buckling load. Okay, which is usually always lower than the one from linear buckling analysis. As a matter of fact, you put the cursor here, you can see that, see this? This buckling load is 7.3, 7.3. You can see that, which is lower than what the other fellow was. Okay. All right. Good luck. That's pretty much it.